This is Module 4, Lecture number 1. So in terms of the test for Module 3, pretty straightforward stuff, some definitions, some questions with respect to, you know, the simple, oh, for crying out loud. There we go, law of definite proportions. Mine isn't operating yet this morning. Those are fairly simple things. I don't think you're going to have any trouble with that. Every year folks have a little bit of problems with the naming. But the instructions are right there in your notes. They're surely in your textbook as well. You just have to remember the differences between naming a ionic compound and a covalent compound, and in order to do that, you got to be able to identify them. So if you will recall, an ionic compound is the combination of a metal and a nonmetal, and a covalent compound is the combination of two nonmetals. And you have to be able to pick them out on your periodic table. So that's the challenges for this module, which to me, you know, I like the pictures. I like the periodic table as something to look at. And so hopefully this will not be too difficult. Was there any questions on Module 3? Before we launch into Module 4? Any questions? Okie dokie. All right, I'll give you some goodies then. Okay. That's not really like pineapple and mango. How's the temperature in here? Of course, I guess it don't matter. I can't do anything about it. Day just got better. Oh yes. Alrighty, you should have 2 pages of these terms, front and back of one, partial of another. Okay, if you would turn with me to page, there we go, page 99. How about that? And we'll do this thing. So you don't have a lot to fill out on your terms this time, as I mentioned to you all along. The point is for you to become familiar with the textbook, and I hope that's happening. I hope you're enjoying reading through, and there's some interesting stuff in terms of this module as well to read through. So again, that's part of the learning process, is just to read through the textbook as well. So let's jump in. This is classifying matter and its changes, and so let's do some tidying first. So we're introducing Module 4 this week. I'm sending you home. That's right, I got to give you my little spiel about days off. I'm sending you home with a test for Module 3. And of course, next week is the fall break, so we won't see one another. And I know how disappointed you are about that. But sadly, we will resume in 2 weeks. But when I was in undergraduate school at the famous Cal College on the Plains, I would find myself at the end of semesters it was almost impossible to learn. And there was a reason for that. Just exhaustion. And if you haven't experienced that yet, you will in your life. But sometimes you just get so tired, you just can't concentrate. You can't learn. And of all things, there was a pastor of the church I attended, and the church was majority students, about 300 and probably 200 students. But anyway, he used to talk a lot about, and I finally got it one time, about the need for rest, and relating that, of course, to the gift of God in terms of the Sabbath. 1 day in 7 is the law. It's right there in the Big Ten, in the moral commands. Take 1 day off in 7. Well, in terms of the Old Covenant, that was Saturday. It was a regular day, and it had to do with a lot of things in Israel. In terms of the New Testament, from my reading of it, it can be any day. I mean, a lot of folks work Sunday. In fact, the Christians in the first century worked on Sunday as well. But the truth of the moral command is still there, the need for rest and the gift of rest. How about a God that gives you a day off every week? All right, that's a pretty neat God. But here's the thing, you need rest. And so I heard that and finally got it, and I began to do it, and I found that I actually did better by not working all 7 days a week, studying and doing whatever I was doing. And I found that I became more productive by getting regular rest. So I wanted you to hear that. I want you to hear that now, because perhaps at this point in your life you're not going to take that seriously like at one point I didn't either. But rest is just such an important part of human physiology. If you take my next course, we'll talk a little bit about that as well. And so when it comes to the breaks, like fall break and then Christmas break, I demand that you not do my classes on those weeks off. In other words, you pick 1 week, either this week or next week, but you pick one of them and you take it off, all right? Because I'm convinced that rest is that important. So even if you're behind, I want you to take a week off from my classes. I mean, again, if your other teachers think differently, that's fine. But, and maybe this is, how can he be so stupid? I mean, of course I'm going to take it off. But surprisingly, some of you are already perhaps in that mode of hitting it all the time. And what I'm telling you is you need to rest from time to time. And so next week, one of those 2 weeks, you're going to take it off. And then when we resume, we will finish Module 4 and you will turn in your test for Module 3. But one of the next 2 weeks, take off. All right? Got it? All right, good. Let's do this. Module 4, I'm reading from your notes. And again, we're classifying matter and it's changed. So this module actually is going to introduce the concept of chemical equations, which we will use. I wonder if I said it. Did I say that the class is, the tests are not cumulative, but the material is. So we're building on the material as we go. So we're going to introduce chemical equations and look at those in this module, but not this week. We'll do that next time. So a pure substance is a substance that contains only one element or compound. All right? So oxygen is a pure substance. It's an element, but another way to describe it is it's a pure substance. So water is that way. The pure water, H2O, that's 2 elements, well, 3 if you count the hydrogens, but that is also a pure substance in the sense that it is just one compound, all right? A mixture is a substance that contains different elements or compounds. So those were defined for you on page 99. Turn over to page 100. And so there's pretty pictures, all right? It's how I learn, looking at the pictures. So notice what they're doing there in terms of the sulfur and iron that's mixed together. And how that mixture can be separated just by use of a magnet. You run a magnet over that mixture and out comes the iron. All right? In terms of these things, to describe those 2 differences in terms of a mixture and a pure substance, here are some statements about it right underneath there in your notes. Compounds and or elements in mixtures do not combine to make new molecules, and that's the example there of the iron and the sulfur. You haven't made anything new, you've just put some stuff together, all right? Compounds and or elements in mixtures retain their individual properties, all right? So in terms of the sulfur and in terms of the iron, you can see that those 2 things are retaining, at least in terms of the metal, the iron, it's maintaining its original property. And just because, go ahead and have your periodic table next to you too, because we will refer to these things. So, all right. Compounds and or elements in mixtures can be physically separated based on their individual properties. So again, in terms of the picture, and it's sort of easy to get the concept by using just one example, but you see that it's relatively easy to separate those 2 based on their individual properties. But then finally, pure substances must be decomposed before their individual components can be separated. So in terms of what happens when you heat iron and sulfur, there's actually a chemical reaction that takes place, and the sulfur and the iron combine to form a new compound. Again, I'm just looking at the picture here on the bottom of page 4.1. They form a new compound, iron sulfide, and once that happens, you see that you can't easily separate the elements in terms of that new compound. Just by virtue of adding energy, adding heat, you've formed a new compound. And when you do that, when you've formed this pure substance of iron sulfide, now you can't easily separate the the elements there. You have to undergo a decomposition reaction. And that's a word that you just heard and you will learn more about in the next few modules. All right, so let me stop there. Is there any questions about the concepts there? So all we're doing now is introducing these concepts in terms of the nature of matter. All right, anything about those definitions that's confusing? Again, I would relate them, any questions you have, to the pictures. The pictures tell 1,000 stories, don't they? Okay, turn over to page 103. All right, there's two definitions, and I've got them both for you in your notes. A homogeneous mixture and a heterogeneous mixture. So a homogeneous mixture is a mixture with a composition that is always the same no matter what part of the sample that you are observing. All right? In terms of an example of that, salt water. So that's a mixture. All right, you actually can separate the salt from the water fairly easily. You just allow a little bit of heat and the salt, of course, will come out of the water. Coke, so if you were to, I don't have any Coke with me and nobody does, but if you were to pour the Coke into the glass, you realize there's lots of stuff in that Coke. Well, in terms of my cool, refreshing beverage, there's lots of stuff in my Diet Mountain Dew. Let's see, carbonated water, concentrated orange juice, citric acid, natural flavor, potassium benzoate, so on we go. But the point is, if I was to pour this into a clear glass and you were to look at it, you couldn't really tell a difference from what's at the top from what's at the bottom, right? So that is a homogeneous mixture. Steel is another example. A heterogeneous mixture, however, is a mixture with a composition that is different depending on what part of the sample that you're observing. And maybe one of the best examples of that, one that I'm sure most of you can immediately see in your mind. Well, actually, you can see it on paper. Turn over to the next page, 104. There it is, the wishbone Italian dressing. That's a classic example of a heterogeneous mixture. In other words, a mixture with a composition that is different depending upon the sample that you're observing. So if you pull that stuff out of the refrigerator or off the cabinet, if you haven't opened, and you look at it and you see, a couple of different layers of stuff in what is supposed to be Italian dressing, right? But you want to eat that on your salad, so what do? You shake it up, and then you pour it onto your salad. And if you were to really be observant, you would notice the same sorts of things happening on your salad as happened in the bottle, and that is stuff would settle, and you would observe a composition that's different depending upon where you're looking at your salad. All right, but the wishbone salad dressing is a classic example in terms of the heterogeneous thing. Now, just as an example of what I've told you too, that sometimes in chemistry, similar things can have, they can be sort of mysterious in the sense of the way they work. So who here, anybody here drink Coca-Cola? Anybody drink Coke or dark pop? All right. So you ever drink it in a clear glass? You ever do that? All right. So you pour yourself up a nice Coke and you're enjoying that thing, and then somebody calls or the doorbell rings and it's a friend, and so you leave that glass sit there and then you go do your thing, and because all of us are in our own ways lazy, you're gone and that Coke just sits there. All right, and in fact, it sits there not for the rest of the day, but it sits there the next day and the next day until finally your mother comes and says, "What is that Coke doing there? It's been there for days." And so, go empty it. And you go and you see your glass, and lo and behold, what's happened to your Coke? Has anybody ever done this incidentally? Anybody? Am I the only one that's been that lazy in my life to have left a glass of Coke sit for days? So if you've done that, what you will notice is there is a settling in the Coke. So the brown, and who knows what else, the sugar perhaps, I don't know, but the brown food coloring that is added to the Coca-Cola has gone to the bottom, and then there's a clear line of stuff, of whatever on top. So what you've done is, by virtue of time, you've allowed what was a homogeneous mixture to become a heterogeneous mixture, in the sense of you no longer can observe the same sort of attributes, the same sort of characteristics in that mixture. So, do these points make sense in terms of these two different kinds of mixtures? And there's examples for you there on page 104 for all the world to see. You can see the difference between pure substances and mixtures, and then how they break them down in terms of pure substances. There's elements, which of course is just a single type of atom, and then compounds, which are combinations of atoms together, and then the homogeneous and heterogeneous mixtures. You'll never look at that Coke the same way after my story of sitting, will you? All right, is there questions about that stuff? Any at all? There's a great discussion on page 105, and I'll just tell you about it real fast. But in terms of, again, we're learning about chemistry, but this is God's world and it's His chemistry. And so it's impossible, really, if you're getting the right kind of education, not to include Him in these concepts. So the air that you breathe, there's a nice little pie graph of the air that you breathe. It's about 21% oxygen. Sometimes, well, maybe you've had courses and you've learned about the composition of air, so you never think of air as pure oxygen. But some of us have thought of air as just being pure oxygen. But if it was pure oxygen, we wouldn't last that long, as a matter of fact. Sadly, if just pure oxygen is actually very detrimental to us if we were just to breathe oxygen. So as it turns out, the air that we breathe is 21% oxygen. It's about 1% other gases, including carbon dioxide, that horrible climate change compound, ozone, argon, and there's other gases as well. Just 1%, though, is the constituent compounds in terms of the rest. But then 78% nitrogen. Now that's strange, you say. I didn't smell any nitrogen just then. No, what was that? Well, yeah, as a matter of fact, you can't smell the nitrogen, but it's 78% of what you breathe in. And as it turns out, nitrogen is completely inert with respect to your body in terms of your physiology. It goes in and it comes out. It does nothing for you and it does nothing to harm you. These other gases, as we mentioned, too much of them and they can harm you, but not nitrogen. And it makes up over 3/4 of the air that you breathe. I mean, if you don't think about these things, that's a miracle. I mean, as far as we know, and astronomers have been looking now for a good number of years. As far as we know, there's no other planet that has an atmosphere like ours. This is absolutely unique. And how did it get here? Well, by chance, by millions and billions of years of chance. It's a beautiful example of how God has made His world. And in terms of the uniqueness of what is needed for you and me to live. So the guy tells the story better than I just did on page 105. Turn over to page 106. So let's introduce two more things. They are underlined and they are in your notes. Chemical change is a change that affects the type of molecules or atoms in a substance, and that's, of course, for the most part, our discussion in chemistry. That's where we're going. We're going to talk about chemical changes. An example of chemical change is burning paper, all right, or that piece of wood that's in your fireplace at home that we're almost, it maybe not too long, we're gonna be able to burn. Isn't that nice? So chemical change cannot be easily reversed, as you well know. If you were to, and you most likely will at the end of this course, you'll take all of these notes and you'll take them to your fireplace and you'll light them on fire and be done with them, right? Well, the problem is if you suddenly go, oh, I wanted to save some of that stuff, it's going to be hard. It's going to be hard to take what has burned and turn that back into your notes, all right? So it's hard to reverse the process of chemical change. And then physical change. So let's contrast physical change to chemical change. That's a change in which the molecule or atoms in a substance stays the same. So the classic example of that is the same paper that you just burned up. Well, instead, I'm going to take out my wrath on this horrible chemistry class and I'm going to rip the notes in half, all right? Well, if you decide later that maybe I wanted to keep those notes after all, you can get out the tape and put those together or put them in a copy machine and produce some new copies. But the point is, the paper hasn't changed in terms of its chemical composition. All you've done is separate some of it that formerly was connected to itself. So the difference then in chemical change is you can't easily put the genie back in the bottle with chemical change, but you can relatively easily reverse physical change. All right? So once again, all we're doing is identifying concepts and sort of defining them and illustrating them. So is there questions about any of that stuff? Okay, let's keep going. Let's talk about phase change. Turn over to page 109. Set your phasers to change. That's pathetic, I know. But, you know. So phase change is this. It's not neatly defined for you on 109, but it's all right in there. So phase change is the process by which a substance changes from one phase, that's solid, liquid, or gas, to another phase, to solid, liquid, or gas. All right? So they got a little sort of diagram there for you, and you can write that down on your notes. I didn't, but you can. So I'm melting is the process by which a substance changes from its solid phase to its liquid phase. Yes, sir?
So is it theoretically possible to have like a solid block of air?
Solid block of hair?
Of air, like oxygen?
A solid block of air, absolutely. Oh yeah. Yeah, if you cool air to the point of it becoming solidified, and I don't know what that temperature is in terms of oxygen's, the formation of a solid, but yes. Great question though, because it's hard to envision that, isn't it? We almost never deal with air in the sense of it being a solid. But if you think about it, then again, we do a little bit, because one of the components of air obviously is water vapor. So we deal with that a lot. Another component is carbon dioxide, and that makes up at least some forms of fire hydrant, the agent that's in a fire hydrant. At least that's what I understand. But maybe I'm wrong about that. I don't know. But the point is, it's hard to envision, isn't it, gases becoming solids, just because that's not their normal phase. And same sort of way in terms of perhaps thinking of steel or iron in its liquid phase. Although, you know, we've seen pictures or maybe video of a steel plant and molten, you know, metals and that sort of thing. So maybe we can grasp that. But great question. Thank you. It was a question, I tell you. And we've got it recorded forever. All right. So melting takes it from solid to liquid. Freezing is the process whereby you change from liquid to solid. Boiling is the process whereby you go from liquid to gas. And so all of you have, whether you've studied that or not, you know exactly what we're talking about in terms of those terms. And so life, in this respect, lines up quite well with what we understand about chemistry. Turn over in your notes. Condensing is the process by which a substance changes from its gas phase to its liquid phase. So, and again, you recognize that too in the sense of if you've boiled water and it condenses into from steam into liquid. So the phases of matter simply describe the three states of matters: solid, liquid, and gas. All right? So again, the first page of notes, the first part of our discussion in this module, is nothing more than, you know, concepts, and not difficult concepts. There's nothing here that you need to stress about, right? Fairly straightforward. So, and if any of them are confusing to you, look at the pictures. That's how we learn. That's how I learn. So, questions about where we've been so far? We're about ready to do a little bit in the direction of some math, sadly. But is there any questions about this stuff? Oh, we're coming up. That's right. We're coming up on page 112. You may as well turn there in terms of the kinetic theory of matter in this sweet little picture of what's going on with atoms or the compounds in terms of various phases. So all substances take up the least amount of volume in the solid phase, except for one. And we're going to talk about that in a second. In the solid phase, and have the greatest density. And the density formula, as Mr. Krabs says, the formula for density shows that, right? In terms of they take up the least amount of volume in the solid phase and have the greatest density. So if mass is over volume, all right, we know that if your volume is smaller and you divide that into mass, you're going to have a larger density, right? And yet also, if your volume is greater, the density is going to decrease, because if you look at the formula, you see what's going on. You're dividing a larger number into that mass number. You haven't changed the amount of mass of whatever you had. You've changed the volume, and so the density is changing, right? So a little more volume, I'm reading from your notes, in their liquid phase, and a little less density. Do you see that in terms of the way it's working with the simple little division equation there? You see it? Anybody not see it? Speak up if you don't. All right. The largest amount of volume is in their gas phase, all right? And that makes sense, right? Again, so you start off with, and I did it. Oh, we are conducting such a chemistry lab, right? So here is my sweet little frozen, I don't know if this is water. There's some gel in here, so they've got some stuff mixed in here to allow it to solidify. So as this thing warms up, what happens is this thing gets floppy, and it although you can see a little bit of space there in terms of the plastic, that actually fills up, all right? Well, if you were to warm it more, the stuff inside there would expand even more. We're going to look at that picture here on page 112. But the point is, you see that in terms of the gas phase, or the warmer something gets, the more the volume expands. All right. Again, we understand that if you boil water. All right. You start off with an amount in a pan, and that keeps expanding in terms of adding heat to it, adding energy, and then of course in terms of the gas escaping in the form of water vapor, you've got an expanded amount of volume. So that's the case, but the exception to this is water. And I don't remember if that long discussion, phase changes in water on page 114 and 115. I'd like for you to read through that just because it's an excellent discussion, and once again it is just a fabulous piece of evidence in terms of the way that God has made his creation. So the exception to this in terms of water is this, and that is, all right, so who's put the glass of water into the freezer because it was warm and you wanted to cool it down, and then you forgot? All right, and or a closed container, maybe a water bottle, and you put that puppy in the freezer, and so what happened? What happened to it?
It froze.
Say what?
It froze.
It froze, and what else? What happened to the container if you had a glass container?
Broke.
Thank you very much. It broke the container. Why did it break the container? Because the glass got too cold? No, because you could put that same glass in that freezer and it would stay there indefinitely. Yes?
Isn't it because the water expands when
Because it is the one compound that has that particular attribute, that quality, and that is that its volume is greater in the solid phase than it is in the liquid phase. How about that? Now, why is that so spectacular? Why is that so unique? Well, as it turns out, if it were opposite, life as we know it could not exist. All right? Now, why is that? Because, well, I even have a stupid example, but let me just tell you the point. So much of the life that we know and we need exists in bodies of water, all right? So if water was like everything else known to man, what would happen is that the water, when temperatures got cold, would freeze, and the solid water, the ice, would sink to the bottom of whatever it was, right? And as a result, slowly but surely, you would freeze the entire body of water, because starting from the bottom going up, you would freeze what's there, and what's ever alive in that body of water would be killed. Now, some bodies of water do freeze over, but that's usually because they're not very deep. But for the most part, a lake that you're familiar with, anybody ever lived up north and ice skated on a frozen lake? Ice fished, which just seems bizarre to me, but anyway. Anybody ever done that? No? So, what happens, of course, is these lakes form, we're getting near the end, solid ice on top, but everything else is insulated underneath. Now, obviously the water's cold, but life, as we know it, is allowed to continue as a result of that insulating property of the frozen water on top of the water. So the whole lake don't freeze. And so all of what we need to continue life is maintained. If water is like everything else known in creation, we don't live. So again, just a fascinating reality to the way God has made his world. So back to page 112. Let's introduce the kinetic theory of matter, and then we'll stop, because I need to bring you up here for your stuff. Kinetic theory of matter is this: the theory that atoms or molecules which make up a substance are in constant motion. Constant. And the higher the temperature, the greater their speed. All right? Greater speed means molecules are moving further apart. All right? And as molecules move further apart, the substance's density decreases. Again, we just sort of looked at it in terms of the density formula. So, kinetic theory of matter simply says that everything that exists, whatever makes it up, is in constant motion. All right? Look at figure 4.4 on page 112. So, in terms of the solid phase, and I've written this stuff for you that is pictured for you on page 112. The solid phase, the atoms or molecules are vibrating back and forth in random directions. All right? So the table that you've got your stuff on, the hard cover of your textbook, they're actually in motion. Hard to see. And I'm glad in terms of having this set up that it'll move across the room, but they're in motion. The matter that makes them up, it's in motion. Now, in terms of the liquid phase, that's a whole lot easier to perceive, isn't it? In terms of the atoms, they're moving about, colliding with one another and the walls of the container. So it's easy to understand that the atoms in a liquid are in constant motion, and certainly that's the case for a gas, right? In the gas phase, the atoms or molecules are moving about faster than in the liquid phase, and they're also much farther apart. So there's the depictions for you, which are obvious, right? In terms of the movement. The one that depicts the solid is less obvious, because again, we just, we don't think of a solid as being in motion, but indeed, the stuff that makes it up is in constant motion. And that's what I've written for you in your notes. The solid phase, the atoms or molecules vibrate back and forth in random directions. The melting point, these are the relating the phases to this kinetic theory of matter. The temperature, the melting point is the temperature at which a substance changes from a solid to a liquid. So we kind of know that, right? If you're melting butter in a pan, you know that whatever that temperature is, that's when it does it. The liquid phase, the atoms and molecules move about, colliding with one another and the walls of their container. The boiling point is the temperature at which a substance changes from liquid to gas. So again, we boil water, you know what that means. And then the gas phase, of course, the atoms or molecules are moving faster than liquids and are much further apart. All right, so we will relate energy to these realities in the modules to come. We're just not today. So obviously it takes energy to get these atoms or molecules moving. So how do you change a piece of ice into a glass of water? So you add energy in the form of heat, right? And the same thing with regards to the gas phase. So we're going to stop there, and then we'll pick it up when we resume. So, alrighty. So the next time, again, in terms of what we're going to jump into is the balanced chemical equations, and that will be in terms of this module, you just got to get that stuff. And so you practice balancing these chemical equations when we introduce them next time, and we'll do good in the rest of the course. Any questions about any of this stuff? All righty. Thank you very much.